Time integration methods can be broadly classified into two categories, namely implicit and explicit methods. Engineers choose between these two types of method based on their computational characteristics, stability, and accuracy for different applications. There are many varieties of time integration methods based on the concept of implicit and explicit. Here, we will explain these two types of time integration methods by their most basic nature. Let's have a look of this 1D function y as a function of time. Assume that we're at a status that all solutions before and include time point tn are known to us. And now we're looking for a solution to the next time step, that is tn plus 1. For explaining the concept of implicit and explicit, we will use the most simplified algorithm to progress from previous time step to the next. We say that the difference between the known and unknown time step is the increment of time delta t times the derivative of the function y dot. In this 1D case, it's just the slope of the function. This is reasonable, right? However, the slope as the derivative of the unknown function, it varies with time. It's not a constant value. In fact, the key to differentiate implicit and explicit method is what to use for the slope in time stepping. Let's have a look. For implicit integration method, it uses the slope at the unknown step tn plus 1 to find next solution. Note that because the function y at the next time step is unknown, the derivative of it is also unknown. Looking at the time stepping equation, on the right side, the previous solution is assumed to be known, but the increment part is unknown. So the results at tn plus 1 is not directly found with this method. That's basically why we call such method implicit, because the result remains implicit after time stepping. We'll need to solve the equation to find the unknown. In many cases, this equation can be nonlinear, and we need to rely on numerical methods such as Newton iterations to solve it. Now, let's move to explicit method. The difference here is explicit method uses the slope at the non-time step tn to find next solution. Because the function y is known at tn, the derivative of it is also known. So in this equation, the right side parts are all directly given. The function y at tn plus 1 is immediately found, or we can say it's explicit. No further effort is needed. I believe this exposes the mystery of implicit and explicit integration method for solving an ODE. To reinforce the understanding, let's solve a very simple ODE by implicit and explicit methods. The given equation is the derivative of function y equals to the sine of y. And the initial condition is at t equals to 0, y0 equals to 1. Now, let's try to find what's the value of y at t equals to 1. Call it y1. First of all, we write down that y1 equals to y0 as the increment between them, which is time step size times the slope of the function. For implicit method, the slope to use is the one at the unknown step, which is the derivative of y1. And by the given ODE, we know that the derivative of it equals to sine of y1. Besides, we know that the time increments delta t is 1 for this problem. So the equation to find the unknown becomes to be y1 equals to 1 plus sine of y1. You can see that the unknown appears in both sides of the equation, so we need to solve this equation to find y at time equals to 1. Now, for explicit method, the story is simpler. Explicit integration uses the slope at the non-step, which is the derivative at y0. By the given ODE, we know that the derivative of y0 equals to sine of y0. You will find that y0 is given as the initial condition, and delta t is known as 1. So the unknown y1 is directly found as 1 plus sine 1 equals to 1.84. To summary, for implicit method, the solution is implicit in the final equation, which needs to be solved. For explicit method, the solution is explicit, that is, directly obtained after time stepping. We've been using first-order ODE to explain implicit and explicit integration methods. move to second-order ODE, the concept is quite similar. Our equation of motion for dynamics is a second-order ODE. When solving the equation of motion, the unknown function y will have physical meaning, which is the deformation, and is conventionally denoted by variable u. In the equation of motion, you can see here we have first-order derivative u dot, the velocity, and second-order derivative u double dot, the acceleration. Since it is second-order differential equation, we need to go one order deeper in the time stepping. So first, for unknown velocity, it equals to previous velocity adding the time step size times the derivatives of velocity. For unknown displacement, it equals to previous displacement adding the time step size times the derivatives of the displacement. So the difference between implicit and explicit method lies on what to use for these two derivatives. If in the final expression, the right side of the equation contains unknown's value, then it's an implicit method. If there is no unknown value for the right side, we can say it's an explicit method. Currently, there are many different time integration methods that have been developed for specific applications, but the basis of them are similar as described here. For more discussion about choice between implicit and explicit methods and how to decide time step size, you'll find it in the next lesson.